Here we have a 100-digit number grouped in 10-digit groupings. We're factoring it using the Alpern number sieve. Gary Alpern wrote it. He updated it in July of this year, 2013. I believe he updated it because people who were format factorization enthusiasts were finding format number factors in his machine, and now it lets you start over every time you do the same number. So that is good and bad. It's bad if you want to show people the factors work on their machine. It's good if you want to show them how long it takes their computer to do it. Here it has found a 12-digit factor, an 8-digit factor, and it has a 93-digit piece left to work on. If you look to the left of the curve number, it's got B1 limit and B2 limit. B1 limit is 1 million, B2 is 100 million. As curves go higher, the number of B limits per curve is more, so the amount of computer work per curve is higher. The computer is pretty much sure it's just about over 25 digits of the next factor. When it gives us the answer, the longest factor is not going to be the one that told us how long it took to do. The second longest factor is going to be the biggest, most work. And the last factor is just going to be a matter of proving that number was prime. If you want to find Alpern's website, you search Google for Alpern ECN. If you wanted to piece the work out of this factorization to more computers, you would type the same 100-digit number in the top box, and then you would type the number in the lower window, 93-digit number at the moment, in the factor box, and you would click on factor. And if that number went down to 67, or if you had a 1,000-digit number and it was 258 or whatever, you would click that in the factor box, and then you would put the number of curves in the new curve box. So here we are working on curve 382. If we were to do that, we would tell one computer to maybe start at curve 1000, and another computer at curve 1500, and another computer at curve 2000. You can even get more work out of one computer that way by having multiple browsers running, or multiple units of one browser, multiple instances of one browser. And each browser would be like its own computer. You would be able to tell it which things. That can keep you as busy as a one-armed paper hanger if it goes through a lot of curves pretty quick. This program does require Java. If you don't have Java installed, it won't run. Before we're finished here, the computer will switch to SIQS, or sieves. This is a self-initialized quadratic sieve. And what the self-initialized quadratic sieve does is it takes the long number, or the factoring number, and instead of starting at the first digit, second digit, third digit, 12th digit, 30th digit, 32nd, 40th digits, it starts at the middle and starts looking from, say, 93 divided by 2 is 46, 47. It will start at 47 digits and start looking its way down, 47, 46, 45. So this number takes about 9 minutes and 40 seconds to factor. I did it a minute ago. And I'm going to show you how to read the results at the end. Ordinarily, the default setting for the digit grouping is 6 digits for people who are copying millions, billions, and trillions. And you have to change that to 10. If you change the number of threads to 4 or 2, it defeats the purpose of having multiple browsers. It doesn't get more work out of a computer, I know from looking at statistics. So we're going to come up with a 67-digit factor here in a second. I rolled this number using 10-digit dice. 10-digit dice are not fair for gambling in Vegas because they can favor one end or the other. 10 digits doesn't piece out regularly over a sphere. But if you use 5 or 10 at a time, now see it switch to seeks, and it's going to take 30 more seconds to be done. If you roll 5 at a time, it's pretty unbiased as long as you don't read the same dice in the same order. You get random numbers that way. And it's base 10. Base 6, you have to convert from base 6 to base 10 to be random for 6-sided dice. So here we see we have a 26-digit factor, and we have a 32-digit factor and a 36-digit factor. Now, for the purposes of verification, if you add up all those factors, it should come up to the sum of the divisors. The sum of the divisors proves you got the factors right. Euler's totient can be used to prove you did the work. And sum of squares, if you take these numbers, A, B, C, and D, and square them, and then add them up, it would come up to a summation that is also used to verify. So you can prove you personally did the work if you record all of those numbers. It's been fun. Talk to you later. Bye.